Welcome back. In this section, we'll be talking about some techniques that can be used to solve quadratic equations. Remember from your earlier math classes that a quadratic equation is one where we've got the highest power for the variable being the power of 2. So any quadratic equation in one variable could be rewritten in this form. Something with x squared plus something with x plus something, where those numbers, the a's, the b's, and the c's, those are all real numbers, and where a is not 0. And the reason we've got that little restriction of a not being 0 was if we allowed a to be 0, then really we wouldn't be talking about a quadratic equation anymore. We'd be talking about something linear. So that's the only restriction that we have there. Now, the idea for solving quadratic equations, one way to solve them is using factoring. Remember that if you have two things that multiply together to give you 0, then that means that one or the other or both need to be 0. This is that zero product property. We use that when we're solving an equation because if we've managed to, for example, rewrite our equation into the form where it's been factored and equal to 0, then we can say, great, well then each of these factors, x minus 3 would be equal to 0, and x minus 5 would be equal to 0. And then we would be able to solve for x. So that's the idea with solving by factoring. We want to see what are the factors of that polynomial, and then once we know what the factors are, then those individual factors can be set equal to 0. Now, couple of cautions here. The zero product property only applies when you have things multiplied together and equal to 0. So if I had something like x minus 3 times x minus 5 equal to x, that's not terribly helpful. That doesn't tell me what x needs to be equal to. The only way that I can conclude immediately what are the values of x that solve this equation would be that if I had it equal to 0. So if we're thinking about solving by factoring, the first move will always be to move all the terms to one side of the equation so that we have 0 on the other side before we start factoring. Now, of course, the other caution is that you know that not everything factors, so just if you're thinking about trying to solve by factoring and it doesn't work, that doesn't mean that there are no solutions. It just means that you'll need some other technique. And we'll talk about some other ways that we can solve quadratic equations apart from factoring. But first, just a couple of quick little examples here. Solving these equations. The first one, x squared equals to 4x. First thing that I'll do, reminding myself I'm not going to divide both sides by x. That might be something you're thinking of doing, but remember, when we're solving an equation, solving by factoring, we're not going to divide out anything that could potentially be equal to 0 because, as we saw in the previous section, that could cause us to lose solutions. So instead, we solve by factoring. So I'll move the 4x to the other side to give me x squared minus 4x equals 0. And now I can take x out as a common factor. And that means I have two solutions then, either that x is 0 or x minus 4 is equal to 0. And from that second little equation, I get the second solution of x being 4. So I can write then, therefore, the solution set is 0 and 4. And I'm going to try to make that look a little bit nicer. A couple of things just as far as notation goes. One thing that you may have seen before, and maybe nobody's explained this to you before what this means, the 3 dots, that's a mathematical shorthand for therefore. So sometimes you'll see this put at the end of a bunch of mathematical work, and so that's somebody summing things up and saying therefore. And what I've got next to it, I have 0 and 4 placed inside of curly brackets. Whenever I'm using curly brackets, like I'm using here, that's to indicate a set or a collection. So therefore, this is the collection of all of my solutions. X can be 0 or x can be 4. Another one to solve, and for this one again, before we start thinking about factoring, we'll want to first rewrite things so that we have all of our terms on one side. So I'll move everybody from the right side of the equation off to the left side. And when I do that, I'll have on the left side now 3x squared. I'll have 19x minus 14, and that's equal to 0. And so I'll try to factor this, and this is that kind of polynomial where I'm going to need to find two numbers that multiply together to give me whatever 3 times negative 14 is. So in other words, I'm looking for numbers that multiply together to give me negative 42. And they have to add up together to give me whatever the coefficient of x is. They have to add up to positive 19. And I can find what my two numbers are. I find my two numbers are positive 21 and negative 2. Those multiply to negative 42, and they do add up to 19. So now I will take that 19x and rewrite it as 21x minus 2x. And then from this point on, I'll factor by grouping. From the first two terms, I can factor out 3x, leaving x plus 7 behind. And from the next two terms, I want to have x plus 7 left behind, and that can happen if I factor out negative 2. So now I've got x plus 7 in both terms. It can be factored out. 3x left behind from the first term, and minus 2 left behind from the second term. So that means I now have two factors, and both of these factors could be equal to 0. So either x plus 7 is equal to 0, which tells us that x is negative 7, or 3x minus 2 is equal to 0, which is that x is positive 2/3. So therefore, for my solution set, I have two values, negative 7 and positive 2/3. One little aside here about solution sets, and sets in general in mathematics. Sets are not in any sort of an order, so there's no order that you have to list the two solutions. If you had said the solution set was 2/3 and negative 7, that would also be correct. And that's true not just here, but if you, for example, take a finite mathematics class and you talk about set theory there, you'll see that topic coming back up again. It sets, there's no order implied when we list things inside of a set. Now, one property that comes to help us out in a bunch of places is this square root property. If you know that something squared is equal to a number, then there are two possibilities. Either that value of a is the positive square root of b, or it's the negative square root of b. So, for example, if you know that x squared is 9, then either x is the positive square root of 9, or x is the negative square root of 9. So you get two solutions, 3 or negative 3. Now, of course, the other thing to keep in mind here is that for roots, this would only be a real number provided what's inside the root is something that's not negative. So if you'd had, for example, x squared equals to negative 9, and you said, well, then x is either the positive root of negative 9 or the negative root of negative 9, that's not a real number, and that's also not a real number, so you would say there are no real solutions. So one thing to keep in mind there is that when we're taking square roots, if we're taking square root of something that's negative, then that's not a real number. So for something like these first couple of examples, we can solve not just by factoring, we can solve using that square root property. The first equation, if I were to bring the 15 to the other side, and then divide everybody by 5, I have x squared is equal to 3, so that means that x needs to be plus or minus the square root of 3. So my solution set then contains positive square root of 3, and it contains the negative square root of 3. For something like example B, x squared plus 1 is equal to 0, x squared is equal to -1, and so if you think about the next step, saying that x is plus or minus the square root of -1, that's not a real number. And so for this, we would say, therefore, there are no real solutions. In a later math class, you'll talk about complex numbers. Later, not the class that you're currently taking, a future one. Complex numbers, those would be the numbers like square root of -1. But for this class, we're only interested in real numbers, so anything that's a square root of a negative, that's not a real number. That won't be a solution that we'll be interested in for this class. All right, and let's do one last one here. This one a little bit more involved. I'm just going to first isolate that little square root that I've got going on there, or sorry, that square that I've got going on there. So I'll bring the 75 to the other side. And before I get any ideas about trying to take square root, I notice it's not just 2x minus 1 squared on the left side. I've also got a 3 in front. So before I start thinking of square rooting things, I'll divide both sides of this equation by 3. And so that I'll have, instead of 3 times 2x minus 1 squared equals 75, I'll have 2x minus 1 squared equals to 25. And so 2x minus 1 needs to be equal to plus or minus the square root of 25, which is just a nice whole number 5. So that means there are two little equations that come out of this. Either 2x minus 1 is equal to positive 5, or 2x minus 1 is equal to negative 5. And at that point, we can now solve for x, taking each equation and solving it individually. So bringing the -1 to the other side and solving for x, bringing the 1 to the other side and solving for x. And I've come up with two solutions for my solution set. X could be 3 or x could be -2. Now, what we did in the last example was actually the last couple of steps that we would be doing when we solve something by completing the square. Remember that when we were talking about completing the square, what that meant was taking something that was quadratic, something like, for example, x squared plus 5x, and we want to turn it into something that can be expressed as a perfect square. And the completing the square part was coming up with that constant term that would turn this from something that was just a quadratic into a quadratic that could be written as something squared. So that's kind of our goal here, is that if we're trying to solve a quadratic equation, we could do it by completing the square. And that once we've completed the square, we would end up with something similar to what we'd have at this step. And that would be something where we could use our square root property to help us out. So the idea to keep in mind when we're completing the square, that when we're looking for what needs to be added in, remember that we would look at whatever the coefficient is for the x term, in this case positive 5. We would cut that coefficient in half to give us 5 halves. Then we would take that and square it to give us 25 fourths. And that would be the amount that would need to be added on so that what we have would be able to be written as the perfect square. And it would be the perfect square x with the half of 5 all squared. So I'm going to now work on completing the square to solve this problem. And I'm going to do this by first bringing that x term to the other side of the equation along with the x squared. So 3x squared plus 4x equals to 1. And before I go further, the one thing for us to remember is that this business of taking the coefficient of x and cutting it in half and squaring it, that begins with us having something that just has x squared, not a coefficient other than 1 in front of the x squared. And we've got that here. We have 3x squared. So really, before I do anything else, I really need to make it just x squared. And I'm going to accomplish that by dividing both sides of the equation by 3. So when we're talking about the completing the square side of things, what we're going to do for our number that we'll need to add in, we'll be taking that coefficient of the x term, which is positive 4/3, cutting it in half. That makes it 2/3. And then that amount, 2/3, we square it to give us 4/9. So that's the amount that I'll need to add in to complete my square. And so when I take my x squared plus 4/3 x, I'll add in 4/9. And of course, if I'm adding 4/9 to one side of the equation, I really need to add 4/9 then to the other side of the equation to balance things out. And that means that what I've got there on the left side is now a perfect square. It is x with half of 4/3, that's 2/3, whole thing squared. And in fact, if you wanted to check this out, if you were to take x plus 2/3 whole thing squared and expand that out, you would find that it does give you x squared plus 4/3 x plus 4/9. On the right side of the equation, I have 1/3 plus 4/9. Using my fraction function on my calculator, I find that that's equal to 7/9. If you haven't already watched the video on using your calculator to do fractions and exponents, that would be a good use of your time, because you don't want to spend a lot of your time doing arithmetic like what is 1/3 plus 4/9 on some scrap paper. You have a calculator that does that for you, so we kind of want to take advantage of that tool that we've got. So now I've got things written as 1 perfect square equal to 7/9, and using my square root property, I have x plus 2/3 should be then equal to plus or minus the square root of 7/9. Now, of course, square root of 7/9 is the same thing as square root of 7 over the square root of 9, and the square root of 9 is just 3. So we have plus or minus, really, root of 7 over 3. And that means then that x is equal to negative 2/3 plus or minus root of 7 over 3. So there are two solutions in my solution set, one of them being negative 2/3 minus root of 7 over 3, and the other one being negative 2/3 plus root of 7 over 3. And of course, before I finish this problem off, it's always good to just double check and make sure that my roots are all simplified. Remember that anytime we see a square root, it needs to be written in simplest terms. Root of 7 already is in simplest terms. There's nothing much else that I could do. The one thing that you could do if you felt like it, and it doesn't really make this any better or any worse, would be to combine these two terms. So for example, instead of negative 2/3 plus root 7 over 3, you could say, well, really, that could be written all as one big fraction, all over 3. Negative 2 plus root 7, all over 3. And you could do the same thing with the first solution as well. You could say, well, instead of two fractions, it's really just one big fraction all over 3.